Okay, we will begin with the eigenspaces. So by definition, an eigenspace of a T, which is an operator, is defined as the null space it's the null space of T minus lambda I. Now, what should be immediate here is that you should recall our previous section where we defined the eigenvalue of an operator as a value, a scalar value, where the null space of this is non-zero. Okay? If it's not the trivial subspace, then this was called an eigenvalue, right? So, so note, if lambda is an eigenvalue of T, then by definition, E of lambda T, which is this null space, is not equal to a trivial subspace. Then in 5.38, it says if lambda 1 through lambda m are distinct eigenvalues of T, then so number 1, E of lambda 1 T plus da 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 E of lambda mt is a direct sum. And secondly, the dimension of each of these eigenspaces has to be less or equal to the entire space. Okay, let's prove this result. So we're going to use an equivalent condition of being a direct sum as 0 can only be written as a unique way, as a 0. Okay, so suppose U1 is from E of lambda 1 T until UM is from E of lambda mt. Okay. And then and U1 plus da 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 UM is equal to 0. Now we already know one choice of such U1 through UM that would make 0, which is 0 for every one of them. Okay. And if there are other vectors that would still satisfy this, with at least one of them non-zero, that would mean that this sum of subspaces is not a direct sum. If we can somehow show that all of these need to be 0, that shows immediately that this is a direct sum. Okay, so let's think about that. Now, what should have been said over here is that if you have any vector that belongs to this eigenspace that's non-zero, that immediately means it's an eigenvector. Okay, so let's just say something over here. So suppose we delete all zeros and leave non-zero ones, okay? Non-zero vectors. From above. So, so that some of them are zero, some of them are, so e.g., it's like 0 is taken out, but let's say u2 is non-zero, okay? And you might have like u5 non-zero, and other things 0, something like this. Okay? This is a horrible way to say it. Sorry, I don't like this. Yeah. Although this is what I want to say. Let's see. Suppose uk is non-zero for some k, k between 1 through n. Okay. Suppose some of these are non-zero. Okay. Then what that immediately means is that uk is in E of lambda kt, which is the null space of t minus lambda k I, which means t minus lambda ki applied to uk is equal to 0. But what does identity do? It doesn't do anything, right? So you get t of uk minus lambda uk equals to 0, which is t of uk equals to lambda times uk, right? What does that mean? That means uk is an eigenvector, right? Is an eigenvector. Okay. So what this says is that thus non-zero vectors of the sum u1 through um equals to 0 are eigenvectors with distinct eigenvalues, right? But then we also learned last time that if you have eigenvectors with distinct eigenvalues, then that list is linearly dependent. So can you have linearly independent vectors adding up to 0? That's impossible, right? Because the only way you can have some linear combinations that add up to 0 is when all the coefficients are 0. You're trying to say that the coefficients are 1 and it's adding up to 0. So that's a contradiction, right? So since eigenvectors with distinct eigenvalues are linearly independent, okay, any non-zero UKs will give us a contradiction. Right? Because one says it's linearly independent and the other says you add them up, you get 0. So how can that be? There's no way. So that says that all ui's, u1 is 0, u2 is 0, all the way until um is 0. And that's exactly the condition for the equivalent condition for sum of subspaces to be direct sum. Okay, and the second part is just a homework question that we already did, just to explain a little bit. If it's a direct sum, then the dimensions just add up, right? But the direct sum is a subspace of the entire space V, and therefore the dimension of the direct sum is less or equal to the dimension of V. But since the dimension of direct sum is the sum of all the dimensions of each vector spaces, we know that this inequality should hold. Okay, so I'm not going to write the separate proof for this. It's just some consequence of a homework question that we did where it showed that if you had direct sum, then the dimensions of the subspaces of the direct sum is equal to the dimension of the entire direct sum. Okay. So, yeah, at some point we are limiting our discussion only to finite dimensional vector spaces. Okay. So T is diagonalizable. And that means there exists some basis where the matrix of T is a diagonal matrix. There exists a list of eigenvectors of T that forms a basis of V. Okay. That's a correct statement. And then there exists U1 through UN that are one-dimensional. T of UK is inside UK. That's my quick way of saying that UK is a invariant subspace of T, of V. That's with respect to T. And V is equal to U1 UN. And D, V is equal to E1 of lambda 1 T plus En of lambda n. E dimension of V is equal to dimension of E1 T plus da 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 dimension of En E. Oh, sorry, I don't know why I put the subscript here. So usually there's in some other books they would define E of lambda 1t as E1 and E of lambda m as En. So that's sorry, kind of got confused. Right? So this is wrong too. Sorry. So it's E of lambda 1t dimension of E of lambda mt. Okay. Where lambda 1 through lambda m are distinct eigenvalues of t. Okay. For dE what does it mean for t to be diagonalizable? It means that m of tb, there's some basis b, so that m of tb looks like a1, or actually lambda 1, lambda 2, da da da, lambda n. And 0 here. That's what it means to be diagonalizable, right? And but then if you write down what that means, it means that see V, so if the basis is equal to V1 through Vn, then see this matrix has the property that if you multiply 1, 0, 0, 0, you get lambda 1 and then 0 everything, right? So this has the property that T of V1 gives you lambda 1 times V1, right? So this holds in general. So having this form is equivalent to saying that the basis looks like this with T of Vk equals to lambda k Vk. And therefore, having a basis of eigenvectors for V is equivalent to saying that there is a basis that makes the matrix of T look like a diagonal matrix. Okay, so this portion shows that A and condition A is equivalent to B. So these are equivalent. Now let me show you how to go from B to C. To go from B to C, we just say define U K as span of Vk. Well, then that means this is clearly one-dimensional, right? And because any vector V in V can be represented as a V equals to C1 V1, Cn Vn, which is well, this is because V1 through Vn, we are assuming B, right? Meaning that we are assuming that there is a basis that looks like V1 through Vn. So since it's a basis, any vector can be represented as a linear combination, which means this would be inside U1 direct sum u2 direct sum da 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 direct sum un, because all of these, each one of these are in the span of each one of these, right? And this representation is unique by the definition of being a basis, and that's what exactly being a direct sum means, right? So this is just immediate after you take the UK as span of VK, okay? Now, how do you show that C implies B? Well, you just, it's also very similar story. Just choose VK from UK with VK non-zero. Okay. Well, because this is one-dimensional, if you choose a non-zero one, then UK would be span of VK immediately, right? And then because V is equal to U1 plus UN, that means any V in V can be written as V equals some U1 plus da 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 UN, with each of the U1 from U1 and U2 from U2, UN from UN, right? That's what it means to be sum of subspaces, right? But then because these are in the, each of these are in the span, each of these are from the span of VK, these are just some C1, V1, Cn, Vn, right? For some coefficient C1 through Cn, because it's in the span. And then, moreover, well, yeah, so you have that, and then because you know that the dimension of V is n, because we already talked about this. If you have a direct sum, the dimension of the entire sum is sum of the dimension of each summand, right? Each of the subspaces that make up the entire vector space, and therefore, what we've done is we found a list that has the length n, same as the dimension of V, that spans the whole thing, so it's a basis. So since V1 through Vn spans V and has length n, it's a basis for V. Okay? So that shows C to B. Now that we've shown that A is equivalent to B and B implies C and C implies B, that shows that A, B, C are all equivalent. Okay. Now the plan for the rest of the proof is to show that B implies D and then D implies E, and then I'm going to show that E implies B. Then it'll be done, right? Okay, so from the previous 5.4, what was it? 5.38, we know that if lambda 1 through lambda m are distinct eigenvalues, then it's a direct sum, right? So we just already showed that. So what's important is that the entire V is made by these guys. So I want to show that if this happens, then this is true. So how do we show that? Well, so for any V in V, because we're assuming that the basis B, there exists something, that's our given, okay? So since we already have a basis V1 through Vn that are eigen vectors, we know that V is equal to A1 V1 plus da 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 A and Vn, since this B is a basis. But then each Vk belongs to some eigenspace lambda j t, because that's our assumption. It's an these are eigenvectors, and any eigenvector belongs to the eigenspace with the eigenvalue, right? So since everything here belongs to something in here, that shows that V belongs to E of lambda 1t, E of lambda mt. So therefore, we've managed to show that V is included in here, but if V is in here, the opposite inclusion is obvious, right? So that shows that V is now equal to E of lambda 1t, E of lambda mt. But furthermore, we also know that this right side is a direct sum, so that's it. Okay. Now D to E is, again, this fact that if you have a direct sum, then the dimensions add up. Okay, so D to E is easy. Okay. Direct consequence of it. So it's a direct consequence of if V is U plus W, then dimension of U plus dimension of W is equal to dimension of V. This. And this is true for arbitrary direct sums. Okay? Okay, and then now how do we show E to B? Well, so suppose dimension of V is equal to dimension of E of lambda 1t, dimension of E of lambda m of t. Okay, let's say we're given this. Then what we do is choose a basis for each E lambda k t, okay, and put them together. To form V1 through Vn. So I know that this n is going to be equal to the dimension of V because of this equality, right? So because the dimensions add up to n, we're assuming n is the dimension of V, that if I choose basis for this guy, basis for next guy, and then put all of them together into a single thing, then we'll have the length n list. Okay. Now we just have to show that either this spans the whole V or this is linearly independent because it's the same size as the dimension. And I'm going to go for showing it's linearly independent. So suppose A1 or C1 V1 plus C2 V2 da 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 Cn Vn is equal to 0. Okay. Then you can combine them into a single vector u1 if they belong to the same eigenspace. Okay, so if this is dimension 2, then you combine the and v1, v2 is from the first eigenspace, then you combine them to get a vector u1. Okay, so you can do that, u2, and then eventually you're going to get um equals to 0. So that each of the u1 through um are from the eigenspaces of lambda 1 through lambda m, right? Well, wait, these are from eigenspaces of different eigenvalues. That was our assumption, right? So we learned before that in that case, well, these are, first of all, these are eigenvectors because these are non-zero. Well, if they are non-zero, then they're eigenvectors, and they are eigenvectors from different eigenvalues. These are eigenvectors of different eigenvalues. Therefore, these are linearly independent. Okay. So again, the same kind of argument that we used for the previous theorem applies here. You have linearly dependent things that add up to 0. Can that happen? No. The only way this is possible is when all of these are equal to 0, right? Yeah. Okay. And if these are 0, then individually they're 0, but then they're forming a basis for each of the spaces. Therefore, each of the C1 through Cn would be 0. It would be all 0. And therefore, this is linearly dependent, and you've shown that this forms a basis. Okay? Okay, so the corollary is that if you have n distinct eigenvalues, then T is diagonalizable. Well, the proof is let V1 through Vn be the list of eigenvectors with the n distinct eigenvalues, lambda 1 through lambda n, right? But that would mean that V1 through Vn is linearly independent. So that would mean that V1 through Vn is a basis because it has the same length as the dimension. Okay? But that's property B in the previous one. And that's equivalent to saying that it's diagonalizable. So it's done. Now, one thing to add here is that, let me pose a question. If you made a computer program to generate an n by n matrix randomly, say 5 by 5 matrix where you make the computer to randomly choose numbers for each entry, okay? What's the probability that you're going to have just two of the eigenvalues being exactly the same, it's going to be 0. Okay. So what's known as this is what's known as an open condition. So yeah. So let me say it like this: if you did the determinant of t minus lambda I, which is not something that the book wants you to know, but this is how you get the eigenvalues, right? And this is a polynomial of degree n, where n is if T is an n by n matrix, okay? And when you choose your entries of the matrix randomly, then the coefficients of this polynomial will also be quite random. And if you have an nth degree randomly generated polynomial, what's the probability that it's going to have a root that's of multiplicity 2 or more? 0, right? Yeah. If you pick random values, if you just pick 2 random values, the probability of those being same would be 0 if you're picking real entries, right? If you're picking numbers from 1 through 10, then the chance of picking 2 numbers and they being equal will be 1 out of 10, right? But if you're picking it from all possible decimal values, then the probability is 0. So what I'm trying to say is that most matrices are diagonalizable, because most matrices will have n distinct solutions of this. And if you have n distinct solution of this, each of these values will be eigenvalues, and then it will satisfy this condition. Okay, so that's what this is implying.